So if we're taking this kind of mega trend of the amount of objects in the sky over the next, I mean, decade, 2 decades, 3 decades, not even to talk about, um, uh, 20, 30 years away from, um, how are the satellites being maneuvered so that they are not going to be colliding with other objects? I had one of my first guests come on, and he was explaining that in certain cases, it's just an email that's being sent back and forth between the operational crews, and they're able to maneuver the satellites so that they don't smack into each other. How much of a reality is this, and kind of what are, I mean, both Scout Space and other organizations looking at to solve this potentially catastrophic problem?
It's not just emails. We actually have some operational software that actually sends text alerts in case of a conjunction.
Mm-hmm.
So there's some pretty good advancement in automation there. But the way that we manage conjunctions, potential collisions, is fundamentally manual. It is on an as needed basis. There's not really a lot of resiliency in the process. People have to figure out where they're going and where the things that are moving towards them going as well. If we have satellite to satellite potential collision concerns, those people need to talk it out, or they need to keep a close eye on each other's satellites so that they don't all avoid in the same direction and potentially cause something even worse to happen.
Mm-hmm. Mm-hmm.
Usually we detect that something is going to be happening a couple days out. And so that leads to a lot of gnashing of teeth and a lot of throwing people at the problem for, let's analyze the scenario and let's figure out how we need to automate to not automate, but let's figure out how to avoid this potential collision. That process is costly, and that process also fundamentally can lead to a lot of different complications, because now you don't have two known satellites that are going their own way. You don't have potential those two satellites changing what directions they're going, which could set them up on a track to potentially collide with other stuff.
Right.
Of course,
right.
we plan for that. Whenever we're planning an avoidance maneuver, we make sure that we're not avoiding into something else. But it's not that easy. It's not that simple. And there's a lot of companies that exist to literally, on a quick turnaround, say, within a couple of hours, tell you, here's how you need to avoid that thing for your satellite operations to be minimally affected. But in the worst case scenarios, we have to deal with stuff having to even have operational downtime to avoid, which means that, well, time is money, especially for some of those big telecom satellites. That's tens of millions of dollars a year. If you have even a couple of hours of downtime, that's expensive, on top of all the engineering time and the fact that we don't have refuelable spacecraft yet, really. So propellant is lifetime on satellites. And so having to avoid something that you don't need to, especially, but I haven't gotten to that yet, really, is really, really costly across the board. And it is done either by outsourcing or by reacting to something that's come to you.
Okay. So then how is Scout Space, your company, dealing with this, right? I mean, I'll have talked about this in the pre-intro. A big part of it is trying to make spacecraft autonomous. Can you touch on that? Can you describe kind of the work that you guys are doing? Because I think it's actually quite interesting, and of course, super valid to the discussion, to the problems that we've been talking about.
Assets in space are between a rock and a hard place right now. They are faced by thousands of objects, hundreds of thousands of objects that we cannot see. We do not know where those objects are or what they are, because they're too small for us to track reliably, but which we should probably be able to avoid if we need to. And all of the objects, tens of thousands of objects, which we know where they are, but don't know precisely enough where they are to reliably know when to avoid them. So one of the most obnoxious parts of how we avoid or mitigate risks in space right now is how many degrees of separation we have from the operator side or from to the spacecraft.
Mm.
If something happens to your spacecraft, you're not going to know what happened to your spacecraft. You're going to know that your telemetry is telling you something weird happened. Or you're going to know that the projection for where your spacecraft is supposed to be overlaps with another projection for where something else is going to be. And so you have to walk that back to, oh yeah, that object and us are going to crash or might crash in a 1 in 1,000, 1 in 10,000 probability. So we need to prepare to avoid it ahead of time. Manually, of course.
Yeah, yeah.
So managing anomalies and managing potential collisions as a manual process is not scalable. Part of why it's not scalable is because there's all these degrees of separation between the actual problem and what we understand. So what Scout is working towards is space-based situational awareness, where a spacecraft itself knows and sees that something is heading towards it. A relative navigation knowledge is very, very different from a propagation of two different objects that are dots of light in actuality moving in weird ways across the sky. And through on-site situational awareness and relative knowledge, we can provide that kind of absolute truth to avoidance requirements. Yes, we know very precisely to within under single-digit meters where an object is going to be and where it is at any given time, which is tens to hundreds of times more precise than we can get from the ground. And we can directly state we can avoid by going this way, and that will, that is a relative navigation scenario that is a lot simpler than, yes, this one object in the sky has an error margin of, or a cone of uncertainty, you could call it, of 5 kilometers. And our conjunction between the two objects is going to get us within 2 kilometers of that object. So we've got two objects that are give or take 5 kilometers in one position in the future, and they're going to be overlapping by 2 kilometers somehow. And yes, you might know where to avoid, but you might over avoid to get out of that cone of uncertainty. We can shrink that cone significantly and provide kind of a truth to the measurement so that can be integrated just seamlessly into the control algorithm. So integrating things like collision avoidance maneuvering capabilities onto satellites is a big part of what we're working to do. And proliferating that across many different satellites is something that we believe will enable space operations as a whole to do that more cleanly. A lot of the uncertainty and a lot of the back and forth that we have to do is based on the fact that we've got humans operating everything from the ground and having to manage these huge amounts of uncertainty. We have to determine what our threshold is for the risk of collision. 1 in 10,000 chance, 1 in 10,000 chance of a collision. That theoretically might mean that 9,999 out of 10,000 times we're actually avoiding something that we didn't need to avoid.
Right.
And we have to make a decision every time. But if we can decrease that uncertainty quotient significantly, that will fundamentally lead to the ability to automate it more easily. And while providing that kind of capability on a satellite inherently doesn't automate the process, it can facilitate automating that process. So we're working with people that are developing automation processes for these systems, and we're also working on our own kind of built-in collision avoidance and relative navigation solutions so that a satellite itself can do these things. SCOUT stands for Spacecraft Observing and Understanding Things. That's the basis for it all. So we think that giving satellites and affording satellites those capabilities is a fundamental step towards automating and facilitating these processes in space.